A quiet morning settles over the Mosul Dam, a silent titan stretching for a mile across the Tigris River in Iraq. The sun glimmers on the still water, obscuring the monumental challenge hidden beneath its surface. 37 years of construction and repairs have left engineers with a singular concern: the dam is leaking, and large portions of the structure remain at risk of failure. Since 1986, a staggering 800,000 tons of grout have been injected into its cracks to mitigate deterioration. For those in the know, every sound is a reminder that beneath this placid surface lies a ticking time bomb of structural inadequacy. How do such vast structures cope when their very foundations are in jeopardy, yet continue to hold back millions of cubic meters of water? In this countdown, we will reveal 8 extraordinary dams that underwent emergency reinforcements, all while remaining in service. Each journey highlights not just the wonders of engineering but the fragility of our greatest infrastructure achievements. As we guide you through this list, you'll meet remarkable machines that carry heavy burdens and the subtle strategies engineers employ to ensure our safety. Prepare to be astonished by answers you never expected. At number 8, we turn to the Warsak Dam in Pakistan, built in the early 1950s. Perched on the Kabul River, this dam has faced numerous challenges over the decades due to sedimentation and water flow fluctuations. In 2013, engineers discovered cracks in the dam's concrete face, revealing a potential for serious failure. As a response, they implemented an emergency reinforcement strategy, injecting cementitious materials to reinforce the stressed areas. They used 3,000 tons of concrete and engineering expertise to bolster the structure, ensuring it could withstand the hydraulic pressure while water surged through its spillway at a rate exceeding 25,000 cubic feet per second. Remarkably, what had been a hidden liability was transformed into a robust structure capable of managing extreme weather events. As we progress to number 7, we bring you the story of the Daniel Johnson Dam in Quebec, Canada. Completed in 1968, it is one of the largest dams in the world by volume, quite literally holding back the mighty Manicouagan Reservoir. When portions of the dam began to show signs of distress less than 3 decades after its construction, it was time to act. Engineers identified issues stemming from instability in the rock formations below the surface that formed the foundations of the dam. In 1996, a meticulous inspection was conducted, leading to an injection of nearly 25,000 tons of concrete to shore up the structure. This rapid reinforcement not only stabilized the base but restored confidence in this behemoth that remains a vital source of hydroelectric power. Reconnecting the risk at hand, let's pause to ask you, which of these machines would you least want to be standing next to? Think about the consequences, and let us know below. Positioned at number 6, the Teton Dam in Idaho is a haunting reminder of what can go wrong when engineering meets environmental unpredictability. After its completion in the early 1970s, it experienced just a few short years of operational life before a catastrophic failure occurred in 1976, leading to a tragic loss of life and devastation in the valley. This event pushed the boundaries of engineering safety protocols, culminating in a new design philosophy aimed at dam safety. The true irony lies in its potential. If emergency reinforcement methods had been better understood, this dam could have been further fortified against the seismic destabilization threats it faced. New regulations ushered in generations of engineers, leading to improved monitoring techniques, which would mandate preemptive actions on dams worldwide. Advancing to our 5th entry, we explore the Oroville Dam in California, famously associated with its 2017 spillway crisis. This incident pushed the dam into the spotlight, forcing the evacuation of nearly 188,000 residents due to fears of catastrophic failure. Engineering teams acted quickly, responding with unconventional measures to stabilize the emergency spillway that had been seriously compromised. They performed repairs using roughly 1 million cubic yards of rock, reshaping the landscape while simultaneously shoring up the structure. This operation demonstrated that a visible threat could spur extraordinary engineering ingenuity, effectively ensuring the dam's viability and safety for future generations. The 4th entry in our countdown leads us to the Kariba Dam, straddling the border between Zambia and Zimbabwe. This colossal structure, completed in 1959, is one of the largest man-made lakes in the world. Yet, as with many grand structures, its impressive list of challenges includes multiple instances of cavitation damage occurring over the years, damage caused by high-velocity water flows striking the spillway. To combat this, engineers have periodically reinforced the spillway structure, fortifying specific areas with specialized concrete and steel reinforcements that withstand intense pressure. The Kariba project serves as a live case study of adaptive engineering practices, proving how attentive maintenance can prolong the life of a dam, even when facing extreme natural forces. At number 3, we delve into the Vajont Dam in Italy, synonymous with tragedy. In the 1960s, a massive landslide not only dislodged 50 million cubic meters of water but also resulted in disaster, an overflowing wave that struck towns below with fatal consequences. The Vajont incident transformed perceptions of dam safety across Europe, prompting engineers to reconsider the nature and management of natural hazards. Emergency interventions were introduced, and remarkably, the dam itself remained structurally sound, leading to discussions about improved monitoring techniques and the importance of real-time data. The consequence of those early missteps echoed through generations, highlighting that understanding surrounding geochemical conditions is crucial for maintaining safety. Now we ascend to number 2 on our countdown. The Oroville Dam again comes into focus, but through a different lens. The spillway failure ignited an incredible response leading to the construction of an entirely new spillway system, a testimony to engineering resilience. Engineers had learned from past mistakes, employing preventive measures that redefined operational strategies for dams all around the world. This fascination with reinvention is indicative of the adaptability that defines exceptional engineering and safety protocols, showcasing that innovation is sometimes born from necessity. And now, the most extreme case we will discuss, the Mosul Dam, a project born from political ambition in the 1980s that remains a living testament to the tension between ambition and stability. The Mosul Dam has been marked by persistent concerns as rainwater infiltrates its weakened system, leading to the infusion of 800,000 tons of grout over the last 37 years. Similar to the lifeblood of the river it serves, this massive undertaking aims to shore up a structure wasting away from within. The real revelation is not simply in the amount of grout injected, but in recognizing the dam's potential for collapse. Engineers, forever aware of the looming consequences, work diligently in the shadows, reinforcing this massive edifice while maintaining its crucial purpose of generating electricity and controlling flooding. As we conclude this journey through the world of dams, it becomes apparent that even the giants of engineering can harbor hidden vulnerabilities. Each entry on our countdown highlights not only the remarkable innovations in engineering but also the unforeseen risks inherent in such immense structures. The treatments and solutions devised for these dams remind us of our capacity for adaptation, a powerful force willing to confront challenges head-on, often out of the sight of the untrained observer. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell us below which machine you want taken apart. Continuing our exploration, let's delve deeper into the stories behind these massive structures and the intricate challenges they present. At number 8, we revisit the Warsak Dam in Pakistan. Built to harness the powerful flows of the Kabul River, this structure is more than a barrier, it's a lifeline. Since its construction, fluctuations in sedimentation and hydraulic pressures have continually tested its integrity. The 2013 emergency reinforcement wasn't just about patching cracks, it involved a comprehensive assessment of the entire structure. Engineers employed a technique called pavement restoration, which included injecting materials like polyurethane foams and concrete into the dam's body, enhancing its resilience against hydraulic forces. With water surging through its spillway at rates exceeding 25,000 cubic feet per second, this dam is now engineered to handle not just typical flows but extraordinary storms as well. The attention to the hidden vulnerabilities of such structures illustrates a profound ongoing commitment to urban risk management, allowing thousands to rely on this engineering marvel daily. As we move to number 7, the Daniel Johnson Dam stands as an icon of energy production, serving Quebec's robust electrical grid. The profound decision to inject 25,000 tons of concrete into this dam wasn't merely a reaction to existing problems, it served a dual purpose. Engineers used a technique called grouting to stabilize not just the main body but key stress points that could foreseeably be impacted by future geological shifts. This precision work ensured that even as external conditions changed, the dam's structural integrity remained intact. The strategy produced long-term benefits. The dam now boasts a record operational lifespan, reinforcing its critical role in generating up to 5,000 megawatts of hydroelectric power, enough to power millions of homes. It is a testament to the foresight that allows engineers to imagine future scenarios and effectively mitigate risks before they materialize. Our countdown now brings us to number 6, where the legacy of the Teton Dam serves as a cautionary tale, a sobering reflection on historical engineering oversight. The catastrophic failure in 1976 led to a death toll of 11 and widespread destruction, a direct result of inadequate assessments of geological conditions. In its aftermath, the engineering community embraced a new era of seismic safety regulations. The Federal Energy Regulatory Commission adopted stricter guidelines around dam designs and reinforced the importance of continuous monitoring. This tragedy led to the implementation of new technologies, such as radar and acoustic monitoring systems, designed to detect any shifts in structural integrity long before they become critical. The vigilance practice today can be traced back to the lessons learned from Teton, showcasing the evolution that occurs from misfortune, transforming fear into rigorous safety standards. Advancing to our fifth entry, the Oroville Dam situation in California cultivated a remarkable story of emergency response and resilience. The 2017 spillway incident was more than a localized crisis, it triggered a reinvention in how engineers approach dam failures internationally. For this dam's reconstruction, teams estimated they would need a staggering 1 million cubic yards of materials to ensure safety, roughly equivalent to the volume of over 200 Olympic swimming pools. The repair strategy involved using innovative materials, such as high-strength concrete enhanced with polymer fibers, to guarantee resistance against the intense hydraulic forces. With the rapid influx of funds and resources, the dam became a live case study not only of failure but of extraordinary recovery. Engineers designed a new, state-of-the-art spillway that can withstand flows exceeding 130,000 cubic feet per second. The speedy recovery efforts transformed initial fears into a model for handling future emergencies, emphasizing agility in engineering practices. Next on our journey is the Kariba Dam, a wondrous structure born from the collaborative efforts of Zambia and Zimbabwe. Spanning over a mile in length and holding back one of the world's largest man-made lakes, it's an engineering ode to human cooperation. Yet, lurking beneath its shimmering surface is the persistent threat of cavitation damage caused by high-velocity flows. In 2017, engineers made sizable investments to shore up the dam's spillway areas, able to withstand fluvial routes sometimes measured in 6,000 cubic meters per second. They achieved this fortification with advanced computational modeling techniques, using simulations to predict stress points in real-time operations. The results of this reinforced spillway have now improved the dam's reliability and efficiency while minimizing erosion, showcasing the power of adaptive engineering strategies. At number 3, the Vajont Dam's narrative presents an indelible impact point in our understanding of geotechnical engineering. The landslide into the reservoir in 1963 remains a sobering reminder of nature's unpredictability. The resulting wave rose over 100 meters, devastating communities downstream. Shockingly, the dam itself adhered to design parameters. It withstood the disaster, prompting an energetic response in the engineering community. In the years that followed, monitoring techniques were vastly re-evaluated. Engineers focused on enhancing data acquisition systems, implementing extensive real-time monitoring capabilities throughout Europe. Technologies such as wire sensors, seismic evaluation systems, and even advanced satellite monitoring ensure that both existing and new structures could be continuously monitored, forecasting any risk posed by geological movements. This transformation turned Vajont into a case study that would overspread into new engineering regulations, safeguarding future projects from similar fates. Approaching our final entry, we once again reflect upon the Oroville Dam amid its innovative resurgence. The project emerged from the 2017 crisis not just as a rebuilt structure but as a redraft of engineering philosophy. The re-engineering of Oroville included constructing a brand new spillway system that utilized cutting-edge technology, including erosion-resistant concrete and dynamically adjustable gates. This ingenuity has redefined operational protocols, instilling within the engineering community a spirit of proactive adaptation rather than reactive mitigation. The success of Oroville stands as proof that adversities, while daunting, can inspire remarkable strides toward engineering perfection. Finally, let's circle back to the Mosul Dam, firmly ensconced at the apex of our countdown. Its construction has perpetually danced with danger since its inception, punctuated by recurrent challenges related to its unique geology. The dam's framework was originally built upon an unsteady foundation of gypsum, which creates an ongoing risk of sinkholes and slippage. However, engineers have more recently deployed techniques akin to the medical efforts of treating a patient, a constant assessment and injection of couplings within the structural geology. Through meticulous grouting, engineers have injected up to 800,000 tons of materials, a feat that's not just about remediation but about preemptive preservation, a fortification process akin to wrapping an ancient scroll in protective casing to ensure its survival for future generations. The ongoing revelations of the Mosul Dam invite appreciation of the delicate balance between human ambition and the natural world, drawing parallels to the way architects balance the grace of aesthetics against the gravity of structural integrity. It's a dynamic dance between engineering prowess and the sometimes unforgiving forces of nature. As we conclude our exploration of these 8 extraordinary dams, each a monument to creativity, resilience, and decisive action, it becomes evident that these engineering marvels require vigilant stewardship. There lies an ever-constant need for innovation and revisitation to ensure they remain safe and functional. These stories remind us that genius lies not solely in creation but also in the vigilance we maintain to protect and adapt. Behind every monumental structure is a story of discovery, loss, and triumph, each revealing the invisible threads of engineering that bind our modern world. Every giant machine hides one piece of engineering nobody notices.